Oh, okay, ma. Sir, shall I start, sir?
Start panel.
Oh, okay, sir. Good evening to one and all present here. I welcome all of you for this webinar on exploring the efficacy and application of small language models. I welcome the speakers, both the speakers, Dr. Sridhar Dasaratha and Dr. Karmvir. Now I request Mr. H.R. Mohan, Chair Events, IEEE CS Madras, to introduce the topic and also the speakers.
Greetings and good evening to one and all. On behalf of the organizing units, Computer Society of India, Chennai chapter, IEEE Computer Society, Madras, ACM Chennai, I have great pleasure in extending a warm welcome to our today's eminent speakers, Dr. Sridhar Dasaratha and Dr. Karmvir Singh Phogat, members and my colleagues from the organizing units and the delegate joined the meeting and those watching the YouTube streaming. The topic of today's presentation, exploring the efficacy and applications of small language models, is highly contextual in the context of the impact of the generative AI models, particularly the LLMs and the foundation models. In today's presentation, the speakers will embark on a comprehensive journey through the world of small language models, popularly known as SLMs, explaining their unique strengths and applications. The presentation will start with an overview of large language models, focusing on the key components that empower their performance, such as vast data sets, intricate architectures, and extensive computational resources. Transitioning to SLMs, the presentation will examine the scenarios where SLMs offer strategic advantages over LLMs. Key benefits such as reduced computational costs, faster inference times, simplicity in deployment, and the capability to operate effectively with domain-specific data will be highlighted. Practical considerations for employing SLMs in various contexts will also be discussed. The session will then explore the methods used to train the SLM, focusing on one of the leading family of SLMs and provide details on the approach and the best practices for fine-tuning the pre-trained SLM for a specific domain and task. The centerpiece of today's presentation will be in-depth analysis of a financial reasoning use case. The section will encompass three critical aspects: leveraging LLM for initial solutions, enhancing the LLM performance through enriching training data and reasoning traces generated by LLMs, and finally employing the synthetic data created by LLM to fine-tune the SLM. This detailed exploration will underscore the symbolic relationship between LLMs and SLMs in solving complex problems efficiently. This insightful session promises to deepen your understanding of small language models and their potential to revolutionize various fields with their targeted and efficient capabilities. Now, I am happy to briefly introduce the speakers. Dr. Sridhar Dasaratha leads a team of AI engineers and researchers at Client Technology E&Y Global Delivery Services. With an extensive expertise in deep learning, natural language processing, and generative AI, he has developed numerous machine learning algorithms and solutions for diverse business applications. In his current role, Dr. Dasaratha focuses on evaluating, applying, and advancing emerging AI technologies, particularly in the realms of generative and agentic AI. His research delves into key aspects of large language models, including retrieval augmented generation systems, fine-tuning domain-specific models, synthetic data, multi-agent systems, and methods for evaluating LLMs. His team has extensively applied and studied LLMs for natural language processing tasks in the financial domain. He has presented his research at multiple conferences, including invited talks. Before joining E&Y, Dr. Dasaratha led research teams in developing pioneering AI solutions across various industries, including security, healthcare, renewable energy, and transportation. Notably, he has directed the creation of unique wind forecasting system, state-of-art pattern recognizing algorithm for security applications, and enhanced early warning system for detecting failures in industrial assets. Dr. Dasaratha is the author of 19 patent filings, of which 9 have been granted. Additionally, he has published 12 papers in leading conferences and journals. Welcome, Dr. Sridhar Dasaratha. Dr. Karmvir Singh Phogat, joining Dr. Sridhar Dasaratha in today's presentation, is a senior AI researcher at Client Technology EY Global Delivery Services. He has expertise in deep learning, natural language processing, generative AI, constraint optimization, and reinforcement learning, with applications across finance, robotics, and aerospace engineering. In his role at EY, Dr. Phogat focuses on delivering and applying advanced AI techniques, particularly retrieval augmented generation, that is popularly known as RAG, fine-tuning language models, multi-agent systems, time series forecasting, and resource planning. Before joining EY, Dr. Phogat held postdoctoral research position at KAIST, South Korea, and the University of Tokyo, Japan, where he developed advanced filtering technique and automatic negotiation algorithm for robotics and autonomous systems. He earned his PhD in systems and control engineering from IIT Bombay, specializing in geometric optimal control theory and for aerospace and electrical engineering. He holds an MSc in applied mathematics from IIT Roorkee with a focus on numerical methods and optimization techniques. Dr. Phogat has authored over 20 publications in leading conferences and journals, contributing to advancements in constraint optimization, Kalman filtering, robotics, and application of generative AI in finance. With this brief on today's presentation and the speaker's introduction, now let me welcome Dr. Sridhar Dasaratha and Dr. Karmvir Singh Phogat to enlighten our participants on SLMs. Over to our speakers, Dr. Sridhar and Dr. Karmvir.
Thank you, Mr. Mohan, for that introduction. So we'll get started. I'll just share my screen to begin with. Can everybody see my screen?
Not yet loaded, sir.
Sridhar, it seems it's not shared. Can you please type in once?
Let me cancel it and try again. Did it work this time?
Yes, Sridhar. It worked.
Okay, so we'll get started. So like it was introduced, what we'll be talking about today is essentially focused on small language models, understanding what they are, how they work, and how effective they are. So I will just go to the outline of the presentation. So before we go into small language models, I will begin with a background on the large language models. And that will set the stage for why small language models will be interesting. And then I'll hand it over to Dr. Karmvir at that point, and he will talk about the 5 family of SLMs, which is pretty interesting to look at because they look at SLMs of they develop SLMs of multiple sizes, and it's insightful to understand how those were developed and what it took to develop those SLMs. So we spend quite a bit of time on that. Then we look at fine tuning, right? So once an SLM is trained or pre-trained, then how do we fine tune it for a specific task? And then finally, we'll wrap up with a case study on the financial question answering. So if I want to solve like a range of diverse problems, so let's think about like maybe I want to summarize a long research article, or I want to write code to automate a task. Maybe I want to translate something. Maybe I want to extract key information from a financial statement. Maybe I want to solve math problems and puzzles. How can I solve all of these diverse set of problems? Well, in today's worlds, the answer is that we can just try solving all of this with a single large language model, right? So that's what makes large language models very powerful, is that irrespective of the nature of the task, which can be quite diverse, very different, I can still try to solve it using a single giant model like GPT-4o, Claude, and many other large models that we have right now. The only thing in theory I need to do is just change the prompt, right? So that's the text I input to interact with the large language model. By appropriately adjusting the prompt, I can essentially apply this language model to try and solve whatever problem that I'm interested in. So large language models offers these benefits. So like I mentioned, I can solve a variety of problems, varied domains, just by changing the prompt. LLMs can understand like a wide range of instructions from these prompts. I don't have to worry too much about tasks. Retraining may not be required. Like in the older machine learning era, we had to retrain for every task. With LLMs, it may not be required. In many cases, it'll already be familiar with what needs to be done. Because I only have to engineer the prompt, it's relatively easy. I can also feed external data or knowledge, my own documents that it can work with. And it depends on the use case, but many times we can get pretty good results or excellent results right out of the box. So here's just a simple example. So like I said, there's different use cases like question answering, code generation. And you can see that, if I'm answering questions from a financial document, I can just give a system prompt saying that you're an expert in financial analysis and answers the question based on some text that's provided. Or I can ask it to generate code, again, by changing just the prompt. I can create content by asking it to be like a math teacher. I can summarize articles, and similarly, I can even run a conversation by asking it to like maybe act as an interviewer. So what makes LLMs so powerful that I can just take it and use it out of the box for so many different and diverse applications. So there are a few key things. The first one is that the amount of knowledge they are exposed to by their training, because many of these models are trained on internet scale data. And the training objective is focused entirely on just next token prediction. So essentially, if I'm given like a few words, what's the next word, right? So it's a pretty straightforward problem in that sense, but then it's done on a very, very large scale with extremely large amounts of data. And through that process, these models acquire significant amount of knowledge about diverse subjects. In addition, there is something known as emergent behaviors, right? So things like in-context learning. With this huge training, what has been observed is that it starts following instructions to some extent, right? Like for example, either I can give an example, like translate English to German, and it can just do it. I mean, without an example, or I can give an example like what's shown on the right side here. I can give an example of what's required and ask it to do it. In addition, to make it like really good at following instructions, there's something called as instruction tuning, which is done on top of the pre-trained model. And that allows it to, or enables the LLM to really use its knowledge and follow instructions more precisely. And that's what made these LLMs very, very powerful, right? And that's the reason we're able to give it instructions on like different topics. And it knows to follow those instructions. It knows how to use or leverage the knowledge it has developed through the pre-training. And hence, it's able to address problems in a variety of domains and use cases. Another aspect of it is not just like fact retrieval. LLMs in some way can reason, right? So here's an example of what's known as chain of thought prompting, which means that I just show it an example of how to solve a math problem, and then I give it another math problem, it can solve it, right? So there's different ways to do that, but I'm just trying to show here that it can do some sort of interesting inferences, not just retrieve facts that it has learned from the knowledge that it's exposed to. And these days, of course, we have models which are specifically targeted to reasoning, both from OpenAI, and we have all heard about DeepSeek are. They're trained specifically to be very, very good at reasoning. Now, moving on for that, if I consider like a few business use cases, oftentimes what can happen is that the domain that I'm interested in can be pretty narrow. So maybe I'm just trying to solve a problem in finance, maybe tax, healthcare, legal. And not only the domain is narrow, sometimes the task can also be very specific, right? Maybe I want to do question answering for a set of documents in tax or some legal documents. Maybe I want to extract information, or I want to do classification, but it might be like a very specific task. So, and I might be interested in executing this task repetitively over a large corpus of documents, invoices, receipts. I'll optimize the prompt for this and then execute it. And then I can get my LLM to work for any of these specific use cases. But the thing to think about is that LLMs, like we talked about, are very great. But do I really need a model with trillion parameters, right? So things like GPT-4 are supposed to have more than a trillion parameters. And do I need such a gigantic model that's trained on so many different domains to be able to answer questions from a very specific and narrow domain, and to work on a very specific task, right? So most likely we will not really use all the knowledge that has been built into the LLM, right? And we may need some of the reasoning abilities, but then again, it may be for a very specialized task. And so it's possible that the cost of these models could be like much more than what I really need to spend and what is really required for like effective performance on these tasks. And we all hear about agentic applications, which can involve like a much higher volume of these calls, LLM calls, and that can further increase the costs, right? And there are other considerations like inference time requirements, right, which may or may not be acceptable depending on the application. And in addition, there is also data privacy and security issues that one has to consider when trying to use LLMs for an application. So that kind of motivates the discussion on SLMs, right? So what are SLMs? SLMs conceptually are still the same thing as LLMs that trained on a lot of data. They have similar architecture, similar principles, but the key difference is they are much, much smaller than LLMs, There is no maybe specific definition of what really is an SLM, but instead of trillions of parameters, one may think of like maybe something which is like a 5 billion, 10 billion, maybe 15 billion, right? But exact number is not important, but the thing is it's like much smaller than these really huge models like GPT-4o. Now, these models can be customized for specific domains and use cases. The inference can be potentially be much faster. Compute requirements can be significantly lower. I don't need large GPU clusters to be able to train those models. So I can just focus on a single task domain that I'm supposed to execute. I can get it to train with like a single or maybe a couple of GPUs. And in addition to that, I can hope to also maintain the accuracy, performance, the reasoning that's required for the specific problem. And in some cases, we can see that they're even better, and we see some examples of that. They can even be better than the LLMs because they're focused, and therefore there's a possibility that they can excel on a specific task and can even outperform an LLM. And finally, because they are small, it brings additional advantages in terms of deployment. I can deploy it on-prem. I can, in theory, put it on a smaller device. Requires some additional manipulation, but I can do it. And I can avoid inferencing from a provider that has a GPU-powered instance in the cloud, right? So these are all the reasons why one may be interested in considering SLMs for a given application. So with that background, I will just hand it over to Dr. Karmvir. So he will talk about like more details on like how these models are built, what it takes to build them. He'll illustrate it through the 5 family of models, which is a range of which has a range of size from 1 billion to 14 billion, right? So we'll get a sense of like how those models were built, what it took to build those models, how they were specialized. And once we complete that, then we'll come back and I'll talk about a financial question answering use case. So I'll stop here, and Karmvir, would be great if you can take over.
Yeah, thank you, Sridhar. So can you see my screen now?
Yes, sir, we can.
Okay. So I'm going to talk about like how we train the small language models, and there are like 2 specific approaches that typically use for training a small language model. One is training from scratch. Okay, so in that what we do is that we have to pre-train the model, and then we have to instruction tune the model. So in pre-training, what typically one does is that one need to initialize the model parameters randomly. And then the model is trained on unlabeled text. So here we don't consider labeled text, and most massive amount of data is required for training these models on the unlabeled text. That is the pre-training approach. What advantage we get here is that we have flexibility to choose the model design. So whatever model design for SLM we want to choose, right, we can do that. But it's an extremely expensive operation because a lot of compute power is required here, and you need a lot of time, and you need a lot of data also. You need to gather a lot of data for this particular stage. In stage 2, what one does is instruction tuning. So these both stages are pretty much the same as Sridhar mentioned for LLMs, right? Instruction tuning, what we do typically is that here model is further trained on labeled data, and that is much smaller data as compared to the unlabeled data that was used for pre-training. And the intent of instruction tuning is to train the model to follow instructions, task-specific instructions. So it could be like zero-shot instructions, few short instructions, right? And it could be, let's say, question answering use case or classification use case, right? Whatever sort of structured output we want, or what sort of response we want, right? It has to be instruction tuned for those specific tasks. So pros here is it will perform the capability of what typically required from the language model. And the cons here is that if the data set is not diverse, right, it may be overfit to the instruction data set that has been used. Another way of using these small language models, right, is knowledge distillation and fine tuning. So training from scratch is quite costly, even though these are small models, but training from scratch gets actually quite costly. So these approaches, what one does is for a specific task, right? Either you can have a labeled data set upfront, and then you can do supervised fine tuning. So in supervised fine tuning for a specific task, we take the labeled data set and then we fine tune the model. So it could be the task could be like sentiment analysis, question answering use case, right? And we can get the model to work for that particular use case. And here advantage would be that a very small model will be able to just reliably perform that particular task, and low compute will be required in the training of supervised fine tuning. The downside here is that we might end up with overfitting to that particular data set if the data set is not diverse, and somewhat generalization will also be lost from the base model where the model was able to perform broader tasks. And another way one can further fine tune the small language model is using knowledge distillation. In this particular approach, what one does is that one create the model, the data using a larger teacher model, and then we distill the smaller model from the teacher model. Now, in this particular approach, we need a nice teacher model which is having far superior capabilities than the student model. That is like a must thing. And then the advantage here is that we will have reduced model with preserving the performance of the larger model for that particular use case. So we'll see both of these approaches. One is like fine tuning and one is training from scratch. So let us move to first approach of training from scratch, and we'll discuss that how 5 family of models have been trained in that fashion, and then how those models have been further improved going from 5.1 to 5.4. So in 5.1, what Microsoft does is that they trained a 1.3 billion parameter model, very small model, just for the sake of experiment and understand that how small models can perform specific tasks. So they are training it for Python coding, and they are using 76 billion tokens at a compute budget. So roughly they have 6 billion training data set, and then they are training for roughly 6 to 7 epochs, 10 to 11 epochs. And then they created this coding assistant. Further, they improved this model with adding more data and more compute budget. Okay, and then this model was able to perform general tasks. So general task in the sense that instead of just doing coding, right, it can do reasoning and math problems as well. Now further, this model was improved, and here for improving this model, right, what they learned is that if they happen to improve the model size, increase the model size and compute budget, right, then the accuracy will further improve. So, and then they found that the phi2 model, which is like double the size of phi1, this is trained roughly on the compute budget is increased by 10 times, and it matches the performance with 70 billion parameter model in certain tasks. So that is like quite stunning, because this model is way small than the 70 billion parameter model, right? So that shows the capability of small language model when we are specializing these models for a specific task. Like these are just are restricted to reasoning, coding, and math instead of general tasks, broader set of tasks. Then phi2 was further improved with phi3, and here they developed 3 variant of phi3: 3.8 billion, 7 billion, 14 billion, and task remains the same because they are fixed on this task. And they have introduced handling long context here, and increase the compute budget also 2.5 to 3.5 times. And they see that further improvement in these tasks. But what they are finding here is that 5.3.14b is not improving to the extent with the model size as ideally it should. And that's why later how they develop 5.4, right? That they added some more specialized techniques for training in 5.4.14b. And 5.4.14b with the further increase of the training compute budget, right, 2 times, they could see that in certain tasks related to question answering for math and reasoning, they found that it matches the performance of GPT-4o. Now I'll talk specifically one by one about these models. So 5.1, the theme was that the good textbook, good quality training data if we use, right, for the training, then less number of data itself might produce really better performance for a specific task. So here you can see that 6 billion tokens they used for the training, and they trained for roughly 4 days with 8 GPUs. So you can see that it's like still a costly affair to train them, even the smaller models from scratch. And they found that once they increase the model size, right, here they trained for 350 million, then further uptrained the same model, and then they increased the model size to 1.3 billion. And then they found that the model accuracy tend to improve with both approaches taken. So one is increasing the model size, and another one is increasing the compute budget, right? So from 26 to 76 they increase, and the accuracy is improving, and model size increase also gives accuracy improvement, right? From 12 to 17 you can say, and so on. So further improved 5.1 to 1.5 for general tasks. So here they incorporated knowledge, reasoning, and code. And this model performs actually quite well. So you see 5.1, 2 variants are there, and they perform quite well as compared to 13B and 7B models for reasoning tasks. Perform actually much better than these models, 13B and 7B model, for these specific use cases. And for other common sense reasoning and language understanding, they get a bit less accuracy as compared to the 7B and 13B models, and quite competitive with the common sense reasoning. So this model was further improved, as I explained, in 5.2, increasing the model size and increasing the training data also. Here they incorporated a lot of synthetic data as well from GPT 3.5. Okay, and so this model was stunning in the sense that it matches the performance of 70B for certain cases. So you can see here that it outperforms 70B. You can see 60, right? And here also accuracy is quite nice when compared with 70B. And other cases also you can see that it does very well. And here it lacks a bit in certain other cases, because this is specialized for reasoning, math, and coding, and 70B is like quite a general purpose model, so it does very well with language understanding and common sense reasoning. Then we have 5.3, where the highlight was that this model can be natively run on iPhone 14 with 4-bit. This can be loaded natively, and this was like a very nice model as compared to the 5.2, because its accuracy is quite nice as compared to 5.2. And there are different variants introduced in 5.3 series. They have come up with vision model and mixture of experts also in this particular series. Then came the 5.4. 5.4, what they do is that they increase the compute budget, and this is 14 billion parameter model. And here you can see that in certain cases it matches the performance of GPT-4. So GPT-4 or even exceeding GPT-4 for performance here, and in this case also. And certain cases it's a bit less as compared to GPT-4, because these are more involved use cases as compared to these one are related to math and general reasoning. And here another highlight is that instead of just doing supervised fine tuning, they also added preference optimization and advanced technique for improving accuracy of these benchmarks. So what we can get from 5 family of model is that these models, the small language models, right, can be specialized to specific tasks. Here we show like reasoning language, math and coding. And if we increase the token size and model size, right, then accuracy improves. That's what we have seen, right? And then 5.3 enables long context handling and introduces multilingual support and vision capabilities. And 5.4 is matching, GPT-4 or performance in certain tasks. So that shows that small language model, if trained for specific tasks, right, can perform at par with what we find in state-of-the-art models, right? GPT-4 is the best so far we get, right? General purpose model, what we have. Now we turn to the second approach, that is SLM fine tuning. So what we have seen is that training from scratch for even SLM is very costly affair. So how we can train a model that is pre-trained and available open source for a specific use case. So here what one does is that we need to define the task as prompt completion pairs, okay? And then we can further fine tune that model. And here I'll talk about that, how we can effectively do that fine tuning of that SLM. So in standard fine tuning, what one does is that people does full fine tuning. And in full fine tuning, these pre-trained weights, right, W, given this input output, right, is updated using gradient procedures, right, using back propagation. And then the whole, all the weights, right, pre-trained weights are being updated. That is like standard regular fine tuning procedure, right? That will be like really costly because you need to update all the weights, even though like these weights are much less as compared to LM, but still it will be very compute intensive task. But what researchers found that if the model size increases, right? So here the number of parameter increases in the model. Then with the model size increase, if we train the model for a specific task, right, then the number of parameters being updated, right? These are number of parameters being updated while training for a specific task, that reduces. So what it means that with very less number of parameter being updated, right, we can still make the model work for a specific use case. Okay, so model can be fine-tuned for a specific use case with less number of parameters. And this motivates that instead of updating this whole matrix of model weights, right, we can have less number of parameters that is defined in terms of this matrix, that is a factor of low rank matrices. And if we update just these matrices, right, we'll be able to get quite competitive performance as we full fine tune the model. And that's why instead of, updating these pre-trained weights, what one does is that one updates these weight matrices. These are very less number of parameters as compared to these ones. So one can say that in certain cases, it will be just 1%. So if this is 1.3 billion, right, it will be just 1% of that. So very less number of parameters one need to train using this approach. And that's why this is very compute effective approach, and it preserves the accuracy, performance also of the model. So here are certain parameters. These are like LoRa hyperparameters one need to set, and they're like standard training hyperparameter. Those are associated with the optimizer. Here we see in the results that the Roberta, right? Roberta large model was full fine-tuned. That was of 335 million parameter model, and it was then the performance was evaluated on multiple tasks, as explained here. And another setting, it was LoRa fine-tuned. Then it is just updating not on 1 million parameters, and accuracy is at par with what you will get with full fine tuning. That is the advantage of this particular technique, LoRa fine tuning. So you can see that accuracy is pretty much matching in all of these tasks. So that shows that the LoRa fine tuning is quite an effective technique, very cost effective, and that too preserving the performance. So here I would like to summarize the LoRa fine tuning. So the LoRa fine tuning means low rank adaptation. And here we are updating very less number of parameters as compared to the regular fine tuning. And it's computationally efficient because we are working with very less number of parameters, roughly 1 or 2% of the parameter. It depends on the use case. And that's why it's less memory intensive as well. We have seen that for various NLP tasks, right? LoRa fine tuning performs quite competitive to the full fine tuning. Now I'll hand over to Sridhar. Sridhar is going to talk about financial question answering use case and how like LoRa fine tuning performs for this particular use case. Sridhar?
Yeah, thanks, Karmvir. So let me share my screen. I hope my screen is visible.
Yes, Sridhar.
Okay. So with that background about pre-training and especially the fine-tuning that Karmvir spoke about, let me now talk about a specific use case, which is around financial question answering. So what exactly is the problem statement here is that suppose I'm given some text and table, right? So the left side shows an image of content from an annual report, right? And I want to be able to answer a question based on the text and information that's provided, right? Now, the way I would need to do it, it's not a very straightforward problem because the question is asking about like change in shares vested. Now, this information is not directly available, right? So I can't just look up shares vested in 2005 and shares vested in 2006 and simply compute the change. The model needs to be able to understand what's being asked for and figure out what is the calculation that's required because the information is not directly available, right? So that's the first thing. It needs to be able to leverage its financial knowledge, figure out what needs to be done. And once it knows what needs to be done, it needs to go and extract the appropriate values, right? So in this case, you can see like, if you look at this 9413, it's a value over here in the text. Similarly, the 8249 is also a value in the text right here. If you look at 20.01 and 9.48, that is in this table here, which is the weighted average value of options granted. So it's a pretty tricky problem for an AI model to solve because of the requirement of the financial knowledge and then the extraction of the entities, and then the fact that the calculation has to be executed with those extracted information. So what we have done is a lot of experiments with this problem where we look at a variety of models, both large and small. The small ones we train by fine-tuning with the approach and the technique that Karmvir just spoke about. Now, to measure the performance of the large language models as well as the small models, and our intent was to see for this complex problem, how close can the small models get to the large models, right? Can they outperform them? Can they at least get close? How does it work if I fine-tune this model? So that was the intent of what we looked at. And we use some publicly available data sets that I've listed here. I won't go into the details, but basically there is data sets which are available, which have like basically the text kind of text that I showed in the previous slide, a question associated with that, and then the answer. So what we can use that for is to train the model, as well as there is test data available to measure the performance of any model that we want to evaluate. So we took those data sets, and then the large models, of course, we can apply it out of the box. The SLMs, we fine-tuned it using the LoRa method that was just described. And we don't have time to get into the hyperparameters discussion, but basically we do have to do some hyperparameter tuning to get this models to work properly for a given use case. That's true of any use case, and we also had to do it for this financial question answering problem. So let's start with like the large language models. So this was from a while back, the original GPT-4 and GPT 3.5 Turbo. Of course, now a lot of improvements have happened, and we have looked at those also, but the performance is roughly the same, right? So this data should still be reasonably be representative of what we can achieve with using a large language model. So how do we use a GPT-4 type of model? Again, like we basically have to optimize the prompt, which is what we have done here. And one thing which is good to do in these kind of cases is that we don't ask GPT-4 to directly produce the answer. We instead ask it to write a Python code to solve the problem. And this is because like LLMs may not be the best to perform calculations, right? So it's better to like write the code which captures the logic that's required to solve the problem. And then we can execute the code to compute the answer. And that's what is essentially what's known as program of thoughts. So combining LLM and this program of thoughts or the Python code creation approach, this is what the performance we got, right? And just to highlight the GPT-4 performance, you can see for FinQA, it's about we getting 78% accuracy. For the TAT-QA dataset, which is somewhat simpler, we get like 93% accuracy. So this gives you an idea of like what is possible with the extremely large models used right out of the box with simply some prompt engineering. Now, to evaluate the SLMs that we have been talking about during the course of this presentation, how well do these perform, right? If I fine tune them, and also how well do they perform without any fine tuning? That's the first question. And then once we fine tune it using the training data that's provided, how well do they work on once they are fine tuned? So one thing we can realize very quickly in these problems is that if I simply give the answer to the question and try to train the SLM, it will not work very well. So the way we have to train, we have to produce training samples which contains the reasoning demonstrations, which in this case is the Python code itself, right? So what it means is that to train the model, so if I have a passage and a question, to train the SLM, I need to first define what the response needs to look like. So how do I get the response? Right? So the response, we use the large language model. So this is kind of the knowledge distillation approach that was talked about earlier. Basically, we have the LLM teach the SLM how to reason out to solve this problem, right? So here I'm showing a simple example where let's say the average credit spread needs to be calculated. So we ask the LLM to write this solution out as a Python code. And then this becomes the output for a given problem that needs to be solved. And we do that for the many examples, training examples that we have in our data set. And then we use that to train the SLM. And we hope that by training the SLM with this particular data set, it can start working pretty well to solve this problem. So how does that approach work, right? Like I said, how do the models look like initially, and how far do we get by this approach of fine-tuning the SLM? So as it turns out in this case, if you notice, like the base model, we tried experimenting with both few shot and zero shot. So what I mean is that without any fine-tuning, we tried to see, we again tried to just use prompting, just like we did with GPT-4. And immediately we can see that some of the models, especially these Orca models, don't work very well. The Mistral model is okay. We get some 41–50% accuracy. The Phi models are a little better. And the Phi 3 medium is pretty decent with 70%. But we can see that none of them out of the box approach like the performance of GPT-4, which is much higher accuracy on this data set. Right now, but if you look at the fine-tuned models, we see that the results are much better, right? So the Mistral model, for example, is close to 76%. The Phi 3 medium is almost the same as GPT-4 after the fine-tuning, right? And this is like a 14 billion parameter model. So mainly what this is showing is that even though this was a fairly complex problem, by this approach of knowledge distillation, we could get the SLM to approach or get to like very close to the performance of GPT-4 And what's interesting here is that it did not seem to matter what the initial performance was, right? So if you look at this like Orca 27B, right? There's a reason why this performance is low initially, because this Orca 2 has been fine-tuned to do something very different. So that's why when we present this particular problem, it looks like it's not working very well. But what's interesting is that when we apply the fine-tuning process, the accuracy for the fine-tuned model, which is this left bar here, is also reaching 71, right? So it's not too far off from the other models. So main conclusion is that, initially these models, the 5 models that we tried to fine-tune, they all look very different, and they're seem fairly falling short of the GPT-4. But once you fine-tune it, they show a lot of improvement over their baseline, irrespective of where they start. And then some of them start getting like very, very close to GPT-4. And the others are not too far away from the performance of GPT-4. So for the conversational, ConfInQA represents a conversational financial question answering data set. In the interest of time, I won't spend too much time on it, but the main point is that the result is the same, right? So once we fine tune it for the conversational question answering type problem, again, we see like big improvements for these SLMs, and their performance again, like if you look at V3 medium, it's at 82%, like very, very close to what we were able to get out of the GPT-4. Now I move to another interesting problem, because one thing that happens with small models, right? We talked about the benefits, but there is a slight disadvantage as well, because all the great things we had with LLM, where we could just take the LLM, straight away start using it, those can go away with the SLM, right? Because I need training data, right? So in this case, there was training data already available, and then we used GPT-4 to enrich the answers with more details on how to solve the problem, and then I trained the SLM. But in a typical case, I may not have that data, right? So what should we do in that case? And how well can I perform in that situation? So to understand that, we looked at fine-tuning SLMs with synthetic data. And just to be clear, what I mean by synthetic data here is that we still use the same financial text that was used for the data sets that I showed. But now I assume that there is no question answer that is available, right? And if I don't have anything, the way I need to solve this problem is that my large model, which is GPT-4, needs to do something more. Not only it needs to produce the detailed explanations for an answer, it needs to create the entire question answer data set. So in other words, it needs to take financial text, it needs to create the question, it needs to write out the answer, and essentially create the entire training data set that the SLM will use. Whereas in the previous one, the questions were already created by a financial expert, the answer was also given, and GPT-4 had just to work out the details of how to solve the problem. But in this case, we don't have anything. So GPT-4 will create the question and create the detailed explanation of how to solve the problem with the Python code. And then we train the SLM with that. So this is roughly the approach, right? So basically, we have raw financial text. The large language model creates the questions in the first step. It also creates the code that's required to solve the problem in a separate step. Some data sets that are created may not be good, but we do only simple filtering of what may be bad data sets. We basically look for cases where the Python code does not execute for some reason, right? So we kind of remove those kind of data points and keep the rest, and then we go ahead and fine tune our SLM. So how well does that work, right? So this slide here shows the results for the TAT-QA dataset and the FinQA dataset. And what I'm comparing here is the performance that was obtained by using the real data, where the questions were already provided, and the numerical answer was also provided, which is what we talked about before. So that is the green bar here, right? So if you look at V3 Mini, for the TAT-QA, with that, I was able to achieve 91% accuracy on the test dataset. Now, when I assumed that no questions were available and GPT-4 had to create the entire question answer dataset, then I got 89% roughly, right? So in this particular case, we get fairly close to the performance of the model that was tuned with the actual data. If you look at FinQA, the results are again decent. for this particular data set, it's like I said, ThinQA is a slightly harder problem than TATQA. So here, the synthetic data model, which was based on the synthetic data, gets decent results, but maybe the difference is a bit more. Like, for example, for the V3 Mini, Phi3 Mini model, there's about like a 5% difference here, right? The medium also has like a 4% difference between like the synthetically created data set and the real data set. But overall, the results are pretty decent, given that the SLM is entirely trained by data that's produced by large language model. So with that, I will conclude the presentation. So what we talked about today was that we started with discussing the LLMs, and what we saw there was the breakthroughs in transformers and LLMs have been really driving the performance of current Gen AI systems. But it comes sometimes at a cost. So because the LLMs, depending on the use case, can be costly. And secondly, they're also compute intensive, which may not be required for every single task. The SLMs are appealing because they, in theory, can achieve maybe the same performance as an LLM, depending on the task, sometimes even better. But what is appealing about them is that their compute needs, when I'm using them for inference, can be substantially lower. And by fine-tuning, I can even, what we saw, the particular use case that we saw in this presentation, with fine-tuning, we can even match the performance of larger models, and they can even imitate the reasoning that's performed by the larger models. And data requirements can be a potential disadvantage of the SLMs, right? Despite all the other advantages, we do have to fine-tune to get it to work properly, depending on the use case. So that can be a disadvantage, but what we saw was that if I use the synthetic data generation, then there's scope to like significantly reduce the burden of that training data that's required. So that's concludes our presentation, and I'm happy to take questions at this point. Thank you.
Thank you for your wonderful session, sir. Now, let me ask the questions that have been posted in the chat box, then the questions from the time of registration. So, Mr. Aditya Karnik has just asked a question. How do you see the potential of SLM as agents, that is task domain specific specialization plus functional calling?
So I think when we are using it in an agentic framework, the same logic applies, right? Basically, if agents are nothing but like I can break up a problem, I can have multiple agents working together, and at the heart of each agent is still an LLM, right, or some sort of a language model, right? And for each of those tasks that the multiple agents are supposed to perform, if we are able to get an SLM to work effectively for that particular task, then I think the SLMs can be equally effective. And the function calling is a separate thing, because I think that's like, we need SLM which is trained to work with a function calling capability, right? So that depends on whether the SLM is trained for that or not. But in general, like if for a specific task, it would just like whatever task each agent is supposed to perform, the SLM would need to be able to perform that task as effectively. And if that's the case, then we can use SLMs as part of agentic solutions. And you also get significant benefit there, because like I said, if when we're using agentic systems, there's often a chance that we call the model multiple times, right? That's how agents work, right? Because they don't necessarily always work in a simple sequence with like a fixed amount of calls to an LLM. They might call it multiple times, and one can potentially get significant benefit with an SLM in that situation.
Thank you, sir. And the same person has asked one more question.
Mm-hmm.
Do you see uptake for SLM in enterprise settings?
So I think that's a good question. So what I see currently, the trend in enterprise settings is still heavy use of the large models, right? And the reason for that is, like, in general, that's a good place to start, right? Because of the issues that are some potential disadvantages that I mentioned for SLMs. So LLMs are, I think, at least from whatever I have seen, they are far more commonly used right now. But SLMs are also being used, right? So maybe like not to the extent that I'm seeing in the LLMs, but because of the specific advantage, especially when like privacy is important or the cost aspect becomes critical, there are use cases which are like significantly relying on SLMs, right? So that's I think my view is that it's uh, LLMs are a lot more widespread just because of the ease of starting with it and putting it into production and starting using it for different use cases. But then SLMs are also being used depending on the use case.
Thank you, sir. Next question from the registration, time of registration. How to apply LLM for society functions like CSI?
So there I would need a little bit more specifics on the question, because like when we say society functions, what kind of tasks are we would that entail, right? Because it really gets down to that, right? So I don't know if the person who asked the question can maybe share a bit more on like what tasks would fall under that, because then it may be better possible for me to give a better answer on like how LLMs and or SLMs can be used for that.
Thank you, sir. Next question. Hello?
Yeah.
Yes, sir.
Mhm.
Yeah. Could you suggest that AI will elevate your deep learning in future education?
Yes. So the way I interpret that question, I hope I'm interpreting it correctly, is that can AI help with education, right? Is it, can it help me understand things better and deepen my learning or sharpen my learning? If that's a question, I think so. That's a very interesting question, because I think in my view, like AI can have two different effects, right? Based on what I've observed as well as how I have played around with GenAI systems. One is that there is a risk one might get a bit lazy, so it could actually impact us in a way that where we are like maybe relying too much on it, not thinking too much. That could be a risk. On the other hand, I've also seen that AI can make us think and work more deeply, right? Like for example, you can even try like having AI work as a tutor, right? So and if you know how to work with the AI, it's actually quite nice, because it will like it can adjust the way it is teaching or explaining concepts to the level that I want, right? So like if I want, let's say I'm looking at some code that's complex, but I've forgotten some basics, right? And while I'm asking it to explain the code, I can ask it to go back and explain some very basic concept, right? So if I use it in a very interactive and thoughtful way, I feel that it can like potentially significantly enhance and help with the learning.
Thank you, sir. Next question. I think this you have answered through your session itself, but anyway, can small language models match large models' performance? How are the challenges of developing? Sorry, what are the challenges of developing small language models?
Yeah, so I think that's related to what we covered. So whether they can match is problem dependent and how they are trained. So in the presentation that we had, like some of the like information that Karmvir showed, there were cases, specific use cases where we saw that the SLM was performing better than the GPT-4, right? Or maybe a substantially larger model, let's say 70 billion parameter model, right? So because of the way it was trained, it actually became better at a specific task. And the reason for that is because SLMs are focused, right? So they are not trying to be good at everything, right? So like the 5 family of models, for example, initially they focused only on coding, right? And then they focused on coding and reasoning, common sense reasoning, math, but it's still a very relatively focused on like what it wants to be good at. So when you do that, then we can certainly see that we will find cases where the SLM can outperform a much larger model, right? And there are other cases like the fine-tuning financial questioning use case, the way we try to do the knowledge distillation. What we essentially did there was we kind of basically taught the SLM using the LLM. And the best we could do was to get the SLM to get very close to the LLM, right? We could not beat the LLM, but we could get it close. And that still has a benefit because of the, the deployment, because I can now use a smaller model, and that might bring some advantages.
Thank you, sir. Next question. All about AI and potential revolution of artificial intelligence in information technology.
So
they are asking. They are
question
asking.
Not very clear to me, please. Can you?
They are asking how the AI is having its potential revolution in information technology.
So I guess the biggest effect we see in AI is of course software development, right? Because like there are so many tools now available to help us write code, and many companies have already talked about how they are writing code much more efficiently. They say things like GitHub Copilot. The productivity of software engineers is much higher with these AI-assisted tools, and I think that's already become a reality. And that's I think where we see significant impact, and will continue to see in the coming future, is that the software development cycles will be much more efficient because of enhanced productivity through the use of these Gen AI enabled tools.
Thank you, sir. Any questions from the participants? Kindly unmute and just ask, please.
I think for legacy systems, can we use the Gen AI?
So, Mr. Mohan, can you be more specific when you say legacy system? So what kind of case? Like converting?
Basically, like converting or retrofitting the thing, something like refactoring.
Yeah. So if you're talking about like code, like software and that kind of thing, like code migration also is a big use case for the LLMs, because one common application I know is like, for example, this when you say legacy systems, right? There are systems which are written or built in SAS, right? And now we may want to get away from SAS and migrate it to PySpark. So I'm not totally sure how well that is working, but I know there are companies which are building solution for converting that legacy code to like a different programming language.
Because that will have a large impact in terms of I think converting the refactoring the existing code.
Yeah, definitely, because that's usually like a very resource intensive effort, especially when you have like extremely large code bases in legacy systems. Converting that to something else, making sure it works as effectively as the previous one is a pretty demanding application.
Correct.
Any more questions?
Yeah, good evening. This is Jaykumar here. Thank you, Sridhar and the team. It was a very insightful presentation. Thanks for that. Actually, my question is, when it comes to the ethical aspects, how does like SLM compare with the LLM? Basically, all this bias, explainability, and that so many responsible AI idea. Is there any is SLMs are better, or how does it run? Can you just throw some light on that, please?
Yeah, I think that's a very good question, and there are many different aspects to it. But one thing I can share, where I think SLMs and LLMs differ significantly, is that the SLM's behavior, I think, is a bit more controlled, and things are also transparent, right? So what I mean by that is, one of the key things with respect to transparency, right, is knowing exactly what it was trained on, right? So for many SLMs, especially because many SLMs are open source, and the amount of information can vary, but one has usually like a reasonable idea of like what went into training that SLM, right? So that is one aspect in terms of transparency. The other thing is, I feel that what is sometimes like a could be seen as a limitation of SLM can also be a benefit. So what I mean by that is, if an SLM for like the 5 models we have seen, right, or some other model, if I've trained it for a very specialized use case, and let's say I want to do something bad to it with prompting, right? I wanted to like maybe write like some false fake news, for example, right? It's hard for it to do that, right? Because it's not, if it's not trained to, it's not trained to do like a lot of fake news or something which is not desirable. It may not be very good at it because because of the small size, because of the data sets that go into training that, it can only learn so much, right? So whereas with LLM, I think the risk can be a bit higher. Now, having said that, of course, the companies which build these very large models, they are constantly trying to put safeguards and protections, guardrails, right, to make sure that the LLMs are used in a responsible way, right? So there's always a lot of work happening there, but I think the risk is also higher because, like, just because of the power they have, I can, in theory, like, or somebody could, like, in theory, manipulate a prompt and make it do something which is not desirable.
Thank you, sir. Thank you.
So
Thank you, sir.
for agentic AI, SLMs are better or LLMs?
So I think it's the same. Gets back to the root task, because if I can, with whatever approach I can get the SLM to work, and I'm able to use that effectively, then SLMs would be then I might as well use my SLMs with the agent, right? But on the other hand, if I prefer the convenience of an LLM, because I don't have to, like, I can just call LLM, start using it right out of the box. So certainly for development speed initially, for any use case, LLMs will always be a faster way to first get going, right, to build an application, because I really don't need to do much, right? I just define my task for the agent. I start calling in an agent, an LLM, which is ready to execute the task. So in that sense, LLM, I think, is like easier to start. And in fact, like, at least it's just my viewpoint. Sometimes, like, especially when I'm looking at a new application, it's easier to first just try it out with an LLM, right? And then address the question of, like, when I want to put it into production or actually use it, then I can address the question of, okay, is this too costly? Can I make it cheaper if I were to use an SLM? Can I actually get an SLM to work effectively? So that question can come later for in many cases.
Basically, the reason is that recently Infosys claims that they have put the invoicing process, agentic process, invoicing, their invoicing and things like that. So ultimately, if it is specific to the particular organization, their SLMs could be better, isn't it? Is it that way or?
Yeah. So that's again very application dependent, because it's so in general for any like domain, right? We have to keep in mind that the GPT-4 is very, like we saw the finance example, right? So for like the use case that I described, it's very specialized, right? It's all about finance, right? But GPT-4 has learned a lot about finance because there's so much financial text available on the internet. GPT-4 has seen all that, so it understands finance pretty well, right? So even though it's a very specialized business use case, but it works really well. Now, but you're absolutely right. There are certain cases where, like, I have some niche documents or niche application, which, let's say, the LLM may not have seen so much data, right? And then it might be worthwhile for me to, like, really build the SLM to kind of learn to work with that. And then SLM becomes, that becomes a big advantage with SLM, because I can train it on my data set. And also, I don't have to send the data out, because if I'm willing to host the infrastructure that's required for that, right? So let's say, I mean, that still is compute intensive, because I may need like 8 or 16 GPUs to train that. So if I'm willing to make that investment, and then I get the benefit that the data stays with me, and I can customize the SLM for my data set, and then use it in whichever fashion I want to.
Thank you, sir. Thank you for your wonderful session. It's my privilege to propose the vote of thanks. So today's session on exploring the efficacy and application of small language models started with Dr. Sridhar stating that solving diverse problems such as summarization, Q&A, etc., using LLM, how it has been done. And he also mentioned about the powerful, what makes LLM powerful, such as the amount of knowledge, then the emergent behavior, and the instruction tuning. And he also spoke about the chain of thought prompting. And he just mentioned then about SLM, which is smaller than LLM and can be customized for specific domains and use cases. And he also spoke about the faster inference. And he also mentioned that it is can be trained easier when compared to LLM, and also can maintain accuracy and performance. And he also mentioned about how it has been can be deployed on prem or smaller devices. He then Mr. Karmvir just started with training language, small language models. He mentioned about two models, pre-training and instruction tuning, and the one with he mentioned, and also with fine tuning, SLM with fine tuning. So he first started with development of Pi family of models. So he mentioned what is Pi 1, Pi 2, Pi 3, and Pi 4. And he mentioned that Pi 3 it can even run on iPhone 14. And he mentioned about the key insights on Pi family, and it's specialized for reasoning and increased training token, and also extended context handling. Then he mentioned about SLM fine tuning. So, and he first started with what is regular fine tuning, and it is costlier. So he just mentioned about the SLM fine tuning, and he just mentioned about the low rank matrices, LoRa and LoRa adaptation. So he just mentioned with the different models how it is performing. Then again, Dr. Sridhar just gave a case study on the financial question answering with the LoRa model. So how the task can be done with the synthetic data and the real data with SLM also, he just explained. So it was, and we had a nice Q&A session also. So he answered all the questions with a detailed note. I thank both the speaker, Dr. Sridhar, and also Dr. Karmvir for the session. And I take this opportunity to thank Mr. H.R. Mohan, Chair, Events, IEEE-CS, and all the societies, joining societies, IEEE-CS, ACM, and CSI for arranging such a sort of webinars. I thank all the participants who participated and asked their queries in the chat box, and also using the mic. And I would like to inform about the forthcoming events. So on 25th of June, we have a webinar on study in the USA, a step-by-step guide for applying to US universities. And also on 16th of July, we have another webinar on choice computing and humanized AI. We can just go to our website, www.csichennai.net, and you can just have a view of the forthcoming webinars and get benefited. Thank you all. Thank you all the participants. Have a nice day. Thank you.
Thank you, Dr. Sridhar and Karmvir. Wonderful presentation.
Thank you. Thank you for having this, for presenting this session. Thank you.
Ma Divya, have you stopped streaming, ma?